Dear students and participants, so in this lecture we'll discuss a very important topic called 4D bioprinting. So this is recently a newly developed technology based on 3D printing. So we'll discuss in this lecture we'll discuss what is 4D bioprinting, what are the technologies that can be considered as 4D bioprinting, and the features of this technology, and also the different applications. And also we'll take a few examples from recent literatures. So let us discuss the first thing, that is what is 4D bioprinting. So this technology was first invented in MIT, and here the fourth dimension. So because earlier we have discussed the 3D bioprinting, so here the another D is added, so 4D. So another dimension, the fourth dimension is here, refers to the time. So if there is a change of the structure after printing, after the printing process, then it can be considered as 4D bioprinting technology. So here the main difference from 3D printing is that it involves a programmable shape change over the post-printing time. Suppose when you print a structure, suppose when you print a structure with any of this 3D printing technique, but then after this 3D printing technique, if the structure changes its shape upon some stimulus, upon some application of some stimulus, then that can be considered as 4D printing. So here, the keyword here is the programmed shape change over post-printing time. So the structure is printed using any of the 3D printing techniques, but there is a shape change after post-printing, and that shape change is programmed or that shape change is anticipated, where the shape change is designed so that that can happen after the post printing process. So 4D bioprinting refers to the group of programmable self-assembly, self-folding, and self-accommodating technology, which include the three main essential components. So here again, please note these keywords. So for 4D bioprinting, also where 4D bioprinting refers to the programmable self-assembly, self-folding, or self-accommodating changes that can happen post-printing. So wherever after 3D printing, wherever there is a programmable self-assembly, self-folding, and self-accommodating changes happen, that can be considered as 4D bioprinting. So please note this. These are the keywords for 4D bioprinting. Again, there are three essential or defining components of 4D bioprinting. What are those? Man-made and not nature-made programmable design. So the whatever the changes that happen, that is not natural. That is programmed or man-made. So somebody has must have designed that so that then only that changes, when the changes happen, then it can be considered as 4D bioprinting. Also, typically, all 2D and 3D bioprinting process can be considered, but along with that, if there is that, say, programmable shape, size, and or volume change happens, then it can be considered photobind. And the post-printing programmable evolving of bioprinted constructs, which could be driven by cells or biomaterials and triggered by an external edge signals. That means if that changes, in case of bioprinted constructs, sometimes the changes can happen upon maturation, but that changes can also be programmable or anticipated, and that changes can be driven by cells or biomaterials, and sometimes can be triggered by external signals. So these all features are all features are necessary for considering one particular technology, 3D printing technology, to be called as 4D bioprinting technology. So in 4D bio, please note down these important points. In 4D bioprinting, there can be programmable self-assembly, self-folding, or self-accommodating changes post-printing. And and all these changes can should be man-made and programmed. That's why it should not be natural changes. And any 2D or 3D bioprinting process can be considered as a 4D bioprinting up if after printing, if we post printing, there are all these processes happens, programmable changes happen. And sometimes the changes can be driven by cells and biomaterials, and that can be, and sometimes the changes can also be triggered by external signals. These all essential components should be there as for in 4D bioprinting. Now let us discuss what are the common features or most important features of 4D bioprinting. Like all other additive manufacturing techniques, 4D bioprinting is not also not a single technology. It's also an umbrella of technologies where all different 3D bioprinting processes can be, or 4D bioprinting strategies can be included. Like we have whatever we have discussed earlier, like extrusion based bioprinting, inkjet based bioprinting, laser assisted bioprinting, and also and some allied technologies. All things can be also can be used or considered for 4D bioprinting technology. So that's why 4D bioprinting is not a single technology like other additive manufacturing techniques. Then the other thing is there should be a man-made programmable design for self-assembly, self-folding, and self-accommodating process. That means if post-printing, if that changes happen within the structure, that changes should be man-made programmable design. That changes based on man-made programmable design. And the changes, like there can be a self-assembly of the construct, so that suppose we have when we put cells within the bioink and we print the structure, then what happens, the cells can assemble together, assemble, and they can there can be a continuous structure development happen. So due to that, the structure can develop from this self-assembly process. So that can be also included in the 4D bioprinting. Also sometimes the self-folding. Suppose we are using certain biomaterials, or where the biomaterials can change its shape or size based on self-folding, based on when suppose when some stimulus is given, that time that self changes can happen. So that can also be can be also included in the 4D biop. Also some self-accommodating processes, like wherever, like suppose the structure is building and the structure upon after stimulus, the structure size got shrunk or maybe got bigger. That kind of changes, self-accommodating processes can also be included within the 4D bioprinting. So this man-made programmable design is another key feature of this 4D bioprinting process. If it is natural change, it cannot be considered as 4D bioprinting. The process of this 4D bioprinting can be stepwise. That can be like related to the type and degree of stimulation, to the type and degree of changes. Suppose the process, like the suppose we first print the structure, then the stimulus is given, then the structure changes its shape. That shape also can be, suppose this can also be a stepwise process. So this all this so that can be also considered for the bioprinting process, if that changes, if that programmable changes can also be, and the programmable changes can also be stepwise. The process, sometimes the process can be reversible or it cannot be it cannot be reversible, but it is always preferred to have the process as reversible, because in that case the changes can be also reversible. That means suppose if certain material that changes its shape, suppose thermoreversible material, so where upon temperature the material can change its shape or size. So that can be also used, that kind of materials can also be used for the bioprinting, and most of the time we call them smart biomaterials because they are sensitive or responsive towards certain stimulus. So that's why they can be very well used for the bioprinting for the bioprinting process. So here, that's the important thing here. The process may or may not be reversible, but it is always preferred to have a reversible process, because then we can have a better control of the process, and we can very well use that for our certain application. Now, the other common feature, more important feature of this technology is that programmable design must be printable. Otherwise, we cannot use that, because here the technology, if you could understand that the technology is basically is 3D printing or 2D printing, but then the changes happen after printing upon some stimulus. So that's why the programmable design must be printable by existing bioprinting processes. So it could be printed in 2D and then folding into 3D, or it can be printed in 3D and then changing its shape into another 3D configuration. Meaning, suppose we printed two-dimensional structures, a film, suppose a film-like structure is printed in two-dimensional. Then, after printing, suppose some stimulus is given, then the structure folded into 3D, folded into tube. So during printing, it is a planar structure. But after printing, when the stimulus is given, that planar structure changes shape to a 3D into a tube like structure to a tube. So that can be a 4D bioprinting process. Other thing is, suppose we print a structure in some 3D configuration, then suppose after the post print, after printing, the structure changes its shape to another 3D configuration. So this change in 3D configuration can happen upon applications of some stimulus, or can be also by other process. So this is also a very important feature of 4D bioprinting, where a programmable design that should be printable by existing bioprinting process. Otherwise, if there is no bioprinting process to print that, then how can I get these structures? How can I get these printed structures? And how can we this process can be the 4D bioprinting can happen. So these all features are very important for 4D bioprinting technology. So the another thing can also be considered for 4D bioprinting is the, if suppose there is a self assembly or self organization that happen through maybe the cellular, it can be a cellular process like cellular self assembly, or can be a material based self assembly or self organization. But these things must not occur naturally, okay, and it must be driven by other cells, biomaterials, and triggered by a external stimulation. So these are like, there can be a post printing self assembly or self organization, that can be a cellular assembly, or can be a biomaterial driven organization or assembly, but those things should not occur naturally. So any programmable change, anything, any anticipated change can be considered for 4D bioprinting. So these are the most common features of 4D bioprinting, as we have said. So this is not a single, as let us again recap this thing. 4D bioprinting is not a single technology. It's an umbrella of technology. All these different types of 3D printing technology can be considered for 4D bioprinting if there is a man-made programmable design that can happen, like say self-assembly, self-folding, a cell accommodating process that can happen post-printing changes. And also the process design for this kind of 4D bioprinting can be stepwise, and also it can be a reversible process, and it can be either 2D printed in 2D, and that 2D can change into a 3D form, or it can be printed in 3D form that can be changed in another 3D configuration. So all these things can be. Another other than this, also self-assembly, self-organization, that cannot be natural or naturally occurring, and it can be man-made or programmable. So these are the most common features of 4D bioprinting. Now let us see what are the different approaches for these changes, like how these changes could happen. and what are the different ways these changes can be manipulated, addressed, or can be used for biomedical applications. Suppose the whenever this suppose this shape change, the shape change can happen by various ways. Either suppose we are printing a two-dimensional structures, a planar structures with supposed with two different biomaterials or two different biowings, more specifically. So where suppose we print with material A, the base layer, and on top of that with material B or a biwing containing cells can be printed on top of that. Now this can be a planar structure while printing, but upon printing, after printing, post printing, suppose when we suppose after post printing, suppose some stimulus is given to it, right? And that stimulus can induce some changes in that. Suppose this structure, this planar structure, start getting folded. So this folding, due to this folding can happen over time, and then suppose if the folding is programmed in such a way, suppose we get a tubular structures after some time. So then this change can be so this process can be called as 4D bioprinting, because here this process, as the earlier the features, please list out the features as we discussed in the earlier slide. Please see that all the features is presented now. This changes is natural, not natural, it's a man-made, this because this design, the choosing of the biomaterials, printing in the particular way, those things are designed. So that because of this a programmable design, it's a programmable change, right? And this change happens after printing. So after the printing is done, then the stimulus is given, then the changes can happen. So that's why this is also under 4D. And another thing is it can be, as I said, the feature, it can be printed in 2D, but then changes its form into 3D. So that is also, while printing it is in the planar structure, but again, so after printing it changes its shape to a tubular structure. So because of all these features, this can be considered as for the bioprinting. Now another thing can happen also, suppose tissue fusion, that self-assembly or self-accommodating process, whatever we have discussed earlier. So those things like the cellular self-assembly suppose happens here, and then we get a continuous tissue structures. Now suppose after the tissue is matured, if there is a shrinkage, so that's why the tissue will be separated from the supporting device. So that this 4D printed tissue, this also can be called as a 4D printed tissue, because this change can happen over time upon stimulus and upon further maturation, and can be here it is driven by cells. It's not natural. It's not natural. It's a programmable change. So that's why this also all this can be. So this all can be considered for the bioprinting. Now there is a size change. Now size change can happen due to different for different reasons. Like suppose we printing a biodegradable device is printed, and then suppose we have implant or printed another structure, a tracheal, suppose the tracheal structure is printed. Now what happened? Decay. This supporting structure can be degraded over time due to the decay in their strength, but the shape can be maintained because the tissue shape can be maintained. Now here the supporting structure, particular device, that is degraded over time, and only the tissue is present here. That tissue again matures, and that can grow upon giving some stimulation. That tissue can grow. So this kind of shape change can also be considered for the bioprinting. Here also, like the tissue is printed in one particular 3D form, and then again the changes in size of the form. So that can happen due to that this, and it is programmable. So due to that, this can also be for the bioprinting. The other thing can happen also, that is typically that is there for self-organization. What happens there? Suppose a microfluid droplets with few cells are present here, like these few cells with microdroplets, those are patterned in a, suppose in a spherical pattern here. What happens? These droplets containing cells, if we control the positioning of these droplets close to each other, leaving only very little gap between these two, then what happens? Cells can sense the presence of other cells nearby, and by this way the cells can assemble, self-assemble with each other. So all these discrete droplets can get assembled with each other, and we can get a continuous tissue structure. But this is driven by the cells, right? Here cells are driving these changes to, so that we are getting a continuous tissue-like structure. So here also, if you see, after printing, during printing is a different like struct different discrete droplets, but after maturation or after this change, post printing changes, this is a continuous tissue like structures. So in this case, the pattern, due to the change in pattern and to the self organization of a stimulation, this kind of structure can happen. This also can qualify for 4D bioprinting. So all these types of changes, either it can be a shape change, it can be a size change, it can be a pattern change. So all these things come under 4D bioprinting. I have taken this example from this published papers. So please go through this paper for further reading and understanding.